In this video, we're going to give a formula for the exterior derivative. So this week, we're going to be talking about the exterior derivative in several different ways. And there's several different approaches you can take to studying it. So the first way will be using local coordinates. Okay, so what is the point of this? So recall that if we have a one form, alpha, so then at any point, alpha is going to take a point in the tangent space to the manifold. I mean, we haven't talked a ton about general manifolds, but we will later. So in general, what a one form does is it takes a vector in the tangent space at a point P to a manifold M and gives you a number, right? So for each vector, it gives you a number. If alpha is a two form, maybe I'll use omega. Then omega at a point P gives you, takes two vectors, each in TPM, and gives you a number. And based on the properties of differential forms, you can show that if alpha is linear, if one forms are linear maps from TPM to R, and two forms are linear maps with certain other properties from the Cartesian product of TPM, two copies of TPM with itself to R. And similarly, so if I have eta is a K form, but here we're not really worried too much about the properties. We're really just thinking about these things sort of as functions. So then eta takes K vectors and sends them to R, right? So there's K copies. So if I sort of want to sort of degeneralize this, what is going on in each of these situations is I'm taking a point and then some number of vectors and getting out a number. So here, for a two form, I take a point and then two vectors, etc. So I can generalize this definition to say a zero form should be a map from sort of zero copies of TPM to R. So that kind of is a little bit of nonsense, but the point is, there's sort of a common denominator every time, which is this point. So what I'm basically talking about is saying that in this analogy, functions should be thought of as zero forms. Okay. And there's something that we know how to do to a function that we don't quite understand how to generalize. So we know how to just take the derivative of a function, but we have this way of turning a function into a one form. So functions can be thought of as zero forms. So I'll use the notation lambda 0 of m as we've been using. So, and if m is Rn, then it would be lambda 0 of Rn. And so what I want to recall is that I have this operator called d, which takes zero forms on Rn and gives me one forms on Rn, right? And the way that I did this, the way that I defined this is df is equal to the sum from I equals 1 to n of df dxi times the operator, times the one form dxi. And because I can think of functions as living in this hierarchy of differential forms, I want to generalize this. So the goal is to generalize d to some function from n forms, or maybe not n forms, let's do k forms, on Rn to k plus 1 forms on Rn. Okay, so how are we going to do this? Well, the first step is that when we define d when k equals 0, it should equal the d of functions, which we're going to do. Then we're going to define what, based on what d does to functions, what it does to forms. So recall that if I have omega, if I've written it as, actually let's do alpha, that's the notation we've been using, sum over I in curly I kn ai dxi, then I should define d of alpha, well, I'll just write d alpha, is the sum over the same number, the same i's, of dai wedge dxi. So what I'm doing is I'm taking, remember, a sub I, these a sub i's are just functions. So these are 0 forms. So then I can take d of them, like I do of a regular function, and then just take the wedge product with dxi. So let's do an example. So here's the definition. And your book writes out this definition as well, using, like you can expand this definition, right? Because I can use the definition of d on a 0 form to expand out what dA sub I should be using that formula. Okay, so an example, if we have alpha is a 1 form on R2, so alpha is equal to a1 dx plus a2 dy, then let's compute what d alpha is. D alpha is, so it should be the sum from I equals 1 to 2 of dA1 by dx times dx plus, sorry, so actually, because I didn't use indices on my coordinates, this will be a little confusing. So I'll just write it out. So it should be d of a1. So the derivative of a1 in terms of x times dx plus the derivative of a1 in terms of y times dy wedge dx plus d of a2. So a2, derivative of a2 by dx plus the derivative of a2 dy wedge dy. And then I can compute what all these wedge products are. And so when I wedge an x with an x, I get 0. So all I'm going to get is dA1 over dy wedge dx plus, and then when I wedge a y with a y, I'll get 0 again. So this will be dA2 by dx, dx wedge dy. And then remember, these are negatives of one another. So what I should end up getting is dA2 by dx minus the derivative of a1 in the direction of dy, dx wedge dy. So that's the first example of how to use this formula to actually take the exterior derivative. And your book has a worked example for an example of a1 and a2. So the final thing we're going to talk about in this video are the properties of the exterior derivative that I can prove using this formula. And we won't prove them all in this video, we'll just prove the first one and you'll do the others for homework. So there's 3 properties of D. So the first one is that if I have 2 forms and I take their sum, then it's as if I took D and then added them. The second one is if I take D of a wedge product of 2 forms. So in this case, let's let alpha and beta are going to be K forms on Rn, and omega is going to be a L form on Rn. Okay, so then then if I take D of a wedge product, then I just get D alpha wedge omega plus -1 to the K, or K, remember alpha is a K form, alpha wedge D omega. And then lastly, D of D alpha is always going to be 0. So let's we'll prove the first one, and I'll show you in this example that we've done the third one. So the proof of the first one, so remember my definition of D alpha. And then my definition of D of a function. So basically what I'm saying is D alpha plus beta is equal to the sum over I d ai plus bi wedge dxi. And then what I need to do now is just show, so it remains to show that dai plus bi is equal to dai plus dbi. And this immediately follows from the linearity of the derivative. So this follows from the fact that dai plus bi by dxi for any I is just the sum of the partial derivatives of ai and bi in terms of xi. Okay, so that's the first one. The other two you'll do for homework. And then for the third one, let's just show an example. So let's take d of d alpha, where alpha is our one form from before. So alpha is a1 dx plus a2 dy. So I computed what d alpha was in the previous example. And let's now take d of this. So what I'm doing now is I take d of this function. I mean, so this is a little bit silly because I'm now taking d of a 2 form, and we know that that should be a 3 form, and there shouldn't be any, there are no 3 forms, non-zero 3 forms on R2. But anyway, we'll just go through the process, so which you can then hopefully see how it generalizes. So this is d of this function, wedge dx, wedge dy. So then I'll be taking d squared a2 dx squared plus minus d squared a1, a1 dy dx plus d squared a2 dx dy minus d squared a1 dy squared dy. And now taking the wedge product with dx wedge dy, and you can see that the x terms will go to 0 because I get a double dx, and the y terms will go to 0. In general, there will be, so in general, maybe I have, so maybe I have a more complicated form. So maybe if I think of alpha as a 1 form on R3, is this any different? Yes, it will be different because I'll be getting some more terms when I take d of a function. But I'll still, so as an exercise, so consider alpha equals a1 dx plus a2 dy as a 1 form on R3, and show that that d of d alpha is equal to 0. And this maybe would be a good exercise to do before trying to prove this general property.